The next type of transfer path we're going to look at is electric fields or capacitive electromagnetic interference. So in this case, the transfer path results from coupling via an electric field that's present between two conductors. And so this is one of the more significant transfer paths that we commonly see in circuits. So we can think about, in general, if we have a voltage difference between two conductors, we're going to get an electric field. So in general, if we have a voltage difference between our conductors, and these can be any two conductors, they can be in the same circuit and different circuit, but what we're going to get with a voltage difference is we're going to get an electric field. And so when we have an electric field, what that's going to do is it's going to produce some net charge Q proportional to the voltage difference. So it produces some net charge Q, which is proportional to the voltage difference between the two conductors. And so, of course, we could talk about sort of simplistically the case for a uniform electric field, where we would have our electric field is represented by E with an arrow on top because it's a vector, is equal to our voltage divided by our distance vector. So the magnitude of our electric field is based on the magnitude of our voltage, and it's inversely proportional to the distance between the two conductors. So if we take a closer look at this net charge Q that's produced between the systems, we can say that the ratio of Q to this voltage is going to have units of farads. So dimensionally, this is equal to farads. And so we know that from our equation, Q equals CV. And so what this means is that we can characterize the capacitance between the conductors. So we can characterize our capacitance between conductors. And so keep in mind, this isn't a discrete capacitor that's in the circuit. This is two adjacent traces or wires or conductors that are interacting via an electric field such that we can characterize that interaction with a capacitor. So when we have some measurable change in charge, that's when we can actually characterize this with a mutual capacitance. So we can say when our voltage difference is resulting, and so this is our voltage difference between two conductors, is resulting in some measurable change in charge. And so of course, if we think back to our basic definition of current, it's just change in charge over time, so dq dt. So if we have some measurable change in charge, that's essentially saying we have some measurable current. So when this is the case, the two conductors have a mutual capacitance. And so we'll look at a simple circuit here in a little bit just to see how we can model that. The two conductors have a mutual capacitance. Okay, and so typically our capacitance E of I, so let me move this up a little bit because we're running into our circuit on the next page. So typically our capacitive EMI is going to be more common in high impedance circuits. So capacitive EMI, more common in high impedance circuits. And so one sort of common example we could say where we would use high impedance circuits is if we're doing low level measurements. So if we're trying to measure really low currents, we would have a high impedance circuit. So let's just say low level current measurements. And so another thing that we could think about too is we could think about maybe some conductor has a large AC voltage, and if it's near another conductor that's connected to sensitive parts of the circuit, then we could have some charge induced on that sensitive area of our circuit, which is going to cause it to operate in a way that we don't intend for it to. Okay, so let's now look at a figure below where we have some amplifier here, and then we have PCB traces. So PCB, so we're assuming this is on a printed circuit board. So printed circuit board traces, so these are essentially the wires on our circuit board that are connecting the various things that we want to connect. And so in this case, our same circuit element is acting as the receiver and the transmitter of the EMI, because if we have a large voltage difference between our input and our output conductor here, we're going to have some mutual capacitance between it. So we can draw that in like this. You can say that has some mutual capacitance C sub m. And so this, of course, is going to be present if we have a large voltage difference with an amplifier. If that has a large gain, then it's very possible that our output will be much higher than our input. So a large voltage difference is going to give us that mutual capacitance Cm. And so this Cm can lead to a couple different types of problems. We can have oscillation at certain frequencies, so instability of our circuit, so oscillation at certain frequencies. And so as we've seen in a previous unit, that's going to happen if our loop gain is greater than 1, so our T is greater than 1, and our phase around our whole feedback loop is equal to 0 degrees or some multiple of 360. The Cm can also result in frequency distortion. And so what this could look like is either peaks or dips in our amplifier's frequency response. And so we've not talked too much about frequency response, but basically it's, of course, making our amplifier behave in ways that we wouldn't expect it to or want it to. So in this case, our receiver and transmitter are on the same circuit, but just a little bit of terminology. If our source and receiver are on different circuits, we have a different name for that type of interference. So our source and receiver are on different circuits. Different circuits, or we could also call it different signal paths. The resulting interference is called crosstalk. And so we could think about if we just had, for instance, if we had another amplifier adjacent to this one, so maybe we had output from some other amplifier coming here, and we had interference between these two, then that would be crosstalk. And so this is just to get you familiar with some terminology. So if we think about ways to avoid this, going back to this basic equation for the case of a uniform electric field, we can see that if we increase this distance, we're going to be decreasing the magnitude of our electric field. So one design solution to prevent this is to physically separate the devices. So one solution to minimize our capacitive EMI is to sufficiently separate our high and low voltage conductors. And so I'm talking about physical separation on our circuit board. So sufficiently separate high level and low level conductors. And so what that means in terms of our circuit up here is maybe instead of having our output trace come here, we could, for instance, get rid of that output trace and we could draw it such that it is staying further away from our input. Or for instance, let's say we get rid of this output here and we just draw it way over here, for instance. And so, of course, an issue we see with this is going to compete with our desire to always be miniaturizing the circuit. So of course we want to make these things as small as possible so that we can fit more things in a certain package and have more processing power or more memory or more whatever it is that we're doing in a certain package. So again, there's always going to be these trade-offs. We want to make sure we don't have excessive capacitive EMI, but at the same time, we can't just expand these things out to make them really large.